So I just wanted to remind you all that, in fact, there is iced coffee here, compliments of the event. So you're welcome to help yourselves. We'd be happy to serve you some. Of course, happy to have you purchase refreshments if that's your choice. It's definitely getting on your clock, so there's that alternative too. And I would just mention that, in fact, the way that we're doing this event at the several establishments is that we, in order to get the space, we didn't buy a block of rooms. We actually simply agreed on a fixed number. So actually, every drink you purchase is actually a donation to the Apache Foundation. So, a good way to look at it. Beyond that, if you are interested in key signing, I will be starting off at 4 o'clock to the printer to print up key signing lists for all the participants who are registered. All you need to know is your keys fingerprint. This is something that you can probably find on your project's website under the keys file. So if you'd like to submit your fingerprint, what we'll do is we'll exchange pieces of paper, or we'll each take on a piece of paper with this list. You will be given a URL to get all the keys to sign. You do this at your own convenience at another time. No PCs are involved in this process at all for the day. So please go, if you'd like to register as one of our committers, please go to S as in Sam, .apache.org/sign, S-I-G-N, all lowercase. So thank you very much for, again, attending today. We'd like to introduce you to Boris Lublinsky, and we're going to learn about student patterns.
Okay, so let's get going. What's the problem? We all love streams, and we're not sure everything has to be done through the streams. The problem is there are all these enterprise databases, services that get in the way of our beautiful stream processing, and somehow we need to incorporate the data from all these places into streams. And here are a couple of examples. We actually stumbled on this pattern by doing model serving, but we figured it's widely applicable for a lot of different things, so let's try to talk about them. So types of additional data that you can have in the stream is either static data, which is relatively simple. You can just cache it as part of your streaming engine. Well, relatively is really a relative term, because if you have a lot of data, it can be quite difficult, because you can quickly run out of memory, but if you have reasonable amount of data, it's not so hard. What is harder is dynamic data, because the data is changing outside of your stream processing, and what do you do with this? How do you update your stream processing to use the new data? So the classic implementation is RPC-based service, which basically means for every item of data that is running through the stream, you do external pull, you get additional data, and you bundle it with stream. So it's good in the sense that people have been using it for the last 500 years or maybe more. And everybody knows how it works, everybody hates it, but people still keep using it. The biggest problem with this is, of course, performance, because for every item of the stream, you have to do external calls, you're doing it over network, you have no idea how network is going to behave. You don't know what your colleagues is going to spoil your networks. Maybe they're pushing for, maybe they're doing something else, and all of a sudden the performance of your stream processing goes completely down. So is there any solution for this? There were several proposals to do it a little bit cleverer, where you do external RPC call and then you try to cache it locally. But this becomes the interesting thing because now you have to synchronize with any updates that are happening externally, and there is no really good way of doing it. This is where dynamically controlled streams pattern came to life. It basically means that you're streaming not only your main data, but all auxiliary data that is used for the stream computation. And here are some references to where this pattern was first published. It was first published by Flink, but you can find references in Spark to the same pattern. So in order for this pattern to be implemented, you have to do log-centric execution. What does this mean? You look at this picture, what does it remind you? It's not at all different. Yeah. It's definitely not data like enterprise service bus, right? But it's not. So this is one thing that I have to strengthen very much because it looks like ESP, but it's a completely different thing. Because in the case of ESP, you were using service bus as kind of interceptor for call to your service. In the log-centric execution architecture, it's more like whiteboard pattern. So all the data that exists in the enterprise is submitted to the set of logs. And when you submit it, you have no idea who is going to use this data. You have no idea how people are going to use this data. You're just saying, okay, I've changed, and this is how I've changed. And when people look at this, immediately they're saying, oh, that's Kafka. It can be Kafka, it can be Pulsar that was talked about yesterday. It can be Akka from EMC. There is quite a few implementations that can be used for this, but the main idea is important. The set of logs, and Nikita, you are actually correct, because you can think about set of logs as their enterprise assets the same way you are treating files in data lake. They are becoming, in effect, the events data lake of your enterprise. So when this is in place, dynamically controlled streams implementation becomes absolutely critical. So you have here the data source that is doing data processing based on the current state, and you can have one or more additional control streams that provide information about any changes in your overall state. So simple enough, right? That's a little bit of the explanation, which I'm not going to repeat. You guys hopefully can read it. So how do you implement it? So it turns out that the pattern itself is generic enough so that you can implement it using any technology. And here I'll show you the examples of how to implement it using Akka streams. Anyone knows what Akka streams is? Dynamically allowed to answer. The company that Valdir and me are working for is called Lightband, and Lightband invented Akka. Well, to be more precise, it took from still. In our opinion, Akka Streams is the best thing on the face of the universe. So, of course, we're using Akka Streams as an example. So the second example is Kafka Streams. So a lot of people that are using Kafka ask the question, okay, why using Kafka? We should use Kafka Streams. This is actually a huge misconception because, yes, Kafka Streams work well with Kafka, but they are cousins. They produced by the same company, but it doesn't mean that if you have Kafka, you can use Kafka Streams, you can use any other streaming engine. I will show you how to do it in Spark, and Joe is not here, but specifically for him, I included Flink examples. So, running example that I'm going to use for everything is temperature control. How many of you get in the shower, try to turn the handle, and the damn thing is switching so fast that either it's too hot or it's too cold? I'm not kidding. This was the first example that I was using in my PhD thesis. How to control the shower. So this is my favorite example, and I'm using it here as well. So this is the definition of how the heater works. And we can look at the implementation. I apologize in advance. I'm using IntelliJ, so font is kind of smallish. Hopefully you can somewhat see it, but yeah, I'm not doing it. Sorry, I know, you're thinking about this. I know, I finally figured out how to use my Mac. Yeah. It took me only 3 years, so I'm kind of slow. If you are interested, the project is called Dynamically Controlled Streams, and it's an open source. You can get it from Lightweight GitHub, and you can take the presentation itself. So it's fairly simple, straightforward. It does exactly what the previous slide was talking about. And to prove that I kind of to prove that I am not lying, I can actually start it. Yeah, he knows me well. And it starts heating up. So one of the things that I'm using here is I'm not running any external Kafka, I'm running embedded Kafka. The code is here in the project as well. This is very convenient if you are doing Kafka-based development. You don't necessarily have to have external one for unit tests. This is absolutely great. So it's running, and you can see that it's heating up a little bit. So we'll let it heat up a little bit, and we come back to the presentation. Let's talk about Akka Streams for a second. So Nikita, you don't need to listen. Everybody else can. Akka Streams is a library that implements reactive streams. One of the nicest features is it's implementing back pressure for flow control. It's also well integrated with the whole Akka framework, including Akka actors, Akka cluster, Akka HTTP, Akka persistence. So pretty much anything that you can think of, you add Akka to it, and and it will be part of the Akka family. It also has Akka friend, which is Alpaca, which is an integration library for a lot of different things. And also, for the longest time, people that were using Akka were complaining that it's not type safe. So this example is done with the latest version, which is Akka type, so it supports type safety.
Boris, could you tip the microphone more toward you because it's directional? Yeah,
Like this?
Yeah, roughly. Now they can hear you better.
Yeah, you can.
Perfect like that.
I'll try to do my best. This is actually a slide that was produced by Honorable Dean Wamper. And it explains the back pressure. So back pressure is a difficult problem that we see everywhere, and there is only one solution for back pressure that existed so far was to put Q in the middle. I mean, if you think about it, Kafka is a back pressure solution. If you don't use Kafka, you can use Q in memory, but this is the problem. So if you try to do a limited queue, things will start falling off the queue because you are filling it very fast. And if you have mismatch between consumer and producer, this is what is going to happen. So people are saying, oh, great, I know the solution, I'll do the infinite queue. And 10 minutes later, they figure out they blow up the memory. So also not the best solution. So what is happening is, you see this little arrow that is going back to the producer, which is saying, dude, I can't take it anymore. Can you stop for a minute and wait for me to catch up? So basically, reactive stream is built-in control for notifying the consumer that, notifying the producer that consumer is lagging behind, and this allows the producer to control the speed with which it is producing data. And the nice thing about it is, if you have a chain of consumer producers, it goes through the chain all the way back. So implementation. When it comes to implementation, it's obvious that for usage of dynamically controlled streams, we need the state. And in the case of Akka family, the state is the actor. So we need to implement the actor that contains the state, which tells it how to properly process the data. And luckily enough, there is a seamless integration between Akka streams and Akka actors. So this is quite simple to implement. So let's maybe take a look at the code again. And here it becomes a little bit more involved. When you implement Akka types, there is one Akka actor type. There is one thing to remember. The type of the actor is defined by the type of the messages that it can consume, which is very convenient because any one of you who was ever doing Akka programming and try to figure out why your actor doesn't see the message that your Akka is sending to him, only to realize 3 hours later that your type is wrong. So Akka type is solving this question, this problem quite nicely, but the way to do it is you have to define all of your messages up front. In a lot of cases, people ask the question, what if my actor consumes more than one message? What's his step? You, it's how you.
You're using traits.
So you have to use trace and then derive every message type that the actor can consume from the tree. So with this in place, they rename things a little bit. So instead of actor itself, the class is now called behavior. But in general, if you did this before, it looks pretty much the same. So you have this on message loop that is picking up the messages from the internal queue and processing them. So enough of theory, let's take a look how it works. So we see that the temperature is going down, but we see that the control was 45 degrees. Something is going wrong. We're not controlling. So let's run the implementation. We see the setting, and we immediately see that the control has been sent back to the heater, and we should be able to see that, the controller realized the temperature is completely out of whack, and temperature is so we will let it run for a while, because while we're talking about Kafka streams implementation, we'll see how the whole thing is changing. But the general idea is quite simple. So the state is effectively the setting that is submitted through the control stream, and the current temperature is submitted through the data stream all the time. And the controller for every temperature that it receives in comparison to the settings, and within within the window, it's switching either to plus or to minus. So very simple, very nice example. So let's look at the next thing. So couple of notes on this which are kind of important. Scalability. Akka streams implementation is a single JVM. So what do we do if there is a lot of data that is coming? So Kafka is your friend. So is any other log implementation, because they all have two notions. They have the notion of topic, and they have the notion of partition. And topic can contain as many partitions as you need. By the way, this is not beer, this is coffee, so I'm going to make it well after. So this actually means a lot of interesting things. How many of you have to use it? Yeah, I'll use both. So one thing to keep in mind, Kafka documentation sometimes is quite deceiving. Because Kafka documentation is saying to you that it preserves sequence. It does, but not on the time level, only on partition level. So when you partition your topic, you have to be very careful. But partitioning is the main mechanism for processing scaling, because every partition can have a single processor, which now means that if you have a very busy stream, you can create multiple partitions out of it, and this will allow you to scale the processes. Resiliency is another important thing, and from this point of view, Akka is unique because Akka has a notion of supervision. You guys know what supervision is, right? You have kids, some of you. So supervision sounds very familiar. So what it basically means that in the hierarchy, if the actor decides to misbehave, his parent kills him. Pretty cruel. But he restarts him. That's reincarnation. That's important. So supervision here make Akka streams implementation extremely fault tolerant because not only you can scale things up and down, but if intermediate things will start going wrong, the supervisor will restart. And if you deploy this on Kubernetes, everybody loves Kubernetes. Right? This is the best thing ever. Not YARN, not COS, Kubernetes is the future. They have the notion of deployers that will watch for the execution and automatically restart if something goes wrong. So you have two kinds of supervision, local and global, and both of them are critical. They will just do it. But reincarnation. So Kafka streams. That was enough on the Akka streams. I'm trying to go quickly through the examples. So Kafka streams is a pretty nice implementation, especially if you have Kafka and nothing else. If you have a more backend system than just Kafka, you might consider using something else. On another hand, Akka streams is by far a better implementation compared to Kafka streams. So Kafka streams has a lot of modern bells and whistles that are used for the stream processing, like windowing, all these good things that are considered to be state of the art in the stream processing. So Kafka streams is pretty good at this. Load balancing is also based on partitioning of that. It's exactly the same because Kafka streams is also a framework, so it's JVM bound by incrementing the amount of partitions. You can run as many JVMs as you want. Kafka streams has two basic primitives, K-streams and K-table. K-stream represents the stream itself. K-table is the implementation of application state. So this is interesting. So what exactly is K-table? It was Jake Krabs, the founder of Confluent, who first started promoting stream table reality, something that we were talking about yesterday a little bit. Because if you know any databases, this is where stream table reality actually takes place, because when you write to the database, you write to the log, which is a stream, and then it updates the table. So K-table that is implemented in Kafka streams support pretty much the same paradigm. So it's the key value table where you can use anything for key, you can use anything for value. It is local, but it's backed up by a Kafka topic, specialized Kafka topic, which is both a blessing and a curse. It's a blessing in the sense that if your particular JVM goes down, or if you get additional listener, then the content of your database might change depending on the keys. So what is happening, it will go back and restore the contents of the table from Kafka topic. So from this point of view, it's absolutely brilliant. What sucks about it is if your application was running for 3 days and the table was updated a million times, guess what is going to happen? You're going to have a million messages on Kafka, and it will take a while to sync up the database to the current state. So from this point of view, it's a little bit more painful than it should be. So let's again switch to the code. Before we look at this implementation, we can see how our temperature was behaving. So it was going up, and then there was a new setting that came here. So it realizes this, and look, it's going up and down. It's covering about 41 degrees that we have set it up. So your shower temperature is good. You can take the shower safe. One thing that I haven't shown to you, which also might be of interest, is how Akka implementation itself looks like, which is surprisingly simple, because Akka streams is effectively a representation of the graph. So most of the people, when they're designing a system, they design them as graphs. And if you design them as graphs, then Akka streams allow you to implement one-to-one. And if you look here, there are basically 2 graphs. One graph is for the new control data, and it's very simple. It gets the record, it maps it, it invokes the actor, and then it doesn't need to do anything with this data anymore. For the actual data, it gets the data, it converts, it invokes the same actor, and then I put a little bit more logic so that it didn't clean every time, it only cleans when something is changed. So enough of this, let's kill him. Let's look at Kafka streams implementation. So the basic implementation is here, and if we look at it, it actually looks quite similar. It's the same basically thing, and we can start it so that we can see how it is behaving and switch to something else. This is actually the interesting thing that I like about Kafka streams. When you start Kafka streams, you can ask it to show you the topology, and it basically prints out the topology like this, so you can kind of guess what you got. The same thing about scalability. The only thing that itself doesn't have supervision, but if you're using Kubernetes deployment, it provides supervision. Flink, too bad Joe is not here. Oh, you're here. So you can do it. Sorry, I didn't notice your.
I want to like sorry.
It's fine. Again, open source stream processing engine, scales well, can run on thousands of nodes, powerful checkpointing and safe pointing that enable full tolerance and restartability. State support, which is very nice, and it also provides all these nice semantics like windowing, things like this. Flink actually was the first one that introduced the pattern because they have this primitive which is called low-level join that is doing exactly what we need to do. So they actually implemented this dynamic control streams pattern. The limitation in Flink, you can have only 2 streams. If you need more, you will have to execute. But that's not really the problem. Flink supports 2 types of joins. It supports key-based join that I'm using here, and it also supports partition join. Didn't always ask me the question why, and I'm sorry, I have to take somebody. That's actually quite simple. If your keys distribution is even, always use key-based join, because key-based join guarantees that the message with the same key is going to be processed by the same instance of the class, which simplifies storage at the state and everything else. For the bad cases, when key distribution is bad, Flink allows you to do round robin, which means that the message with the same key can be processed in any executor. It evens the load. It allows you to prevent the hard servers. So code pretty much the same. I will probably skip it because we're probably getting close on the time. Let's.
You have another 15 minutes. You probably want about 4 minutes a slide, depending on how many questions you expect.
Right. Quality pretty good. One important difference between Flink and Akka streams and Kafka streams. Flink is doing split internally, so instead of individual partitions, you get all of them. And this is kind of important. If you need to process all partitions simultaneously, you need to use either Spark or Flink. Spark is the interesting one. Spark is so far the 600-pound gorilla, but the more we're using Spark, the more we're realizing that no matter how great Spark is for bad jobs, for streaming jobs, it's probably not the best choice. So what can you do in Spark? structured streaming is the latest and greatest thing, which means that everything is SQL-based, and Spark SQL is supposed to rule the world. So the way it operates is like this. It's based on the same stream-to-table duality. So as the stream propagates, the table starts to grow, and obviously Spark takes care of checking the beginning of the table so that it gives only part of it. So stateful processing in Spark is a little bit complex. Problem, and I'll talk about this in the subsequent slides, but the basic idea is Spark streaming is cheating. It's not really streaming, it's mini batch. And every mini batch is recreating executors, which means that all the states has to be external. So because of this, they've introduced map with state and map group with state that works something like this, where the state is stored externally from the executor and then pushed to the executor for every execution. So I can show you the code, but in this particular case, I will choose not to because there is a couple of interesting things that is coming. So Spark structured streaming came up with a new idea of continuous processing, which will make it into true stream processing engine, which looks great on paper. In reality, it doesn't quite work. The problem with this is that you can't use this continuous processing regime with any of the complex transformation. If you do any of the complex transformation and try to use it, Spark very politely will tell you, but no, I can't do this. So this thing was still bugging me, and with the help of a friend of mine who came up with kind of hack, which actually works quite nicely. And that's why I was giving the code, because I wanted to show you this. So what is happening here is there are two loops. One loop is the data loop. And this is implemented using classical Spark streaming. And what this thing does is every time when the data update comes, it interrupts continuous execution and stores it into the storage. The storage is on the driver. Here the assumption that the amount of storage data is not that great, so we can store it on the driver. And this is a continuous loop that pretty much does nothing. It gives the new data, it's doing map with the state. The state in this case is local because Spark will bring it to the executor, and you can run continuous streaming like this. So again, kind of boilerplate. So this is probably the most important one. When you are talking about streaming, you have to realize two fundamental differences between Spark and Flink. In Flink, iterations are executed as cyclic data flows, which means you will get a couple of things, but don't do it. So this basically means that all the allocation is done up front, which has an interesting caveat. The caveat is all the local memory is preserved between iterations. In Spark, the implementation is completely different because for each iteration, a new set of tasks for executors is going to be created that will be involved, which means that the only place to store intermediate data between calculation is outside. That's why they've implemented microstate and all this machinery to have additional RDT or data frames to store the data that they can read into the new iteration. And this makes streaming, especially state streaming in Spark, by far more expensive, because you have to stream data back and forth between external storage and the execution. That's basically what this slide said. And there is additional thing in Spark structure streaming, because SQL is great. Raise your hand who doesn't like SQL. The problem with SQL is SQL data types. So if you're using Spark structure streaming, it means that the only data types that you can use are SQL data types, which makes any complex structure easy to deal with. Because yes, there is a way out. You can represent them as byte array, but in this case, SQL engine is completely useless because it has no idea how to deal with it. So dynamically control streams are great. Love them, use them. And thank you very much. I didn't intend.
Okay, we've got time for 5 minutes left for questions. If anybody has any.
I'm sure it was not very yours.